Hi everyone. So, I am back with yet another lecture, and this time we are going to continue on the topic that we have been discussing in last few lectures, which is on ultrasonic testing. So, before we proceed, let us see quickly what we have learned so far. Till last class, this is what we had. We first discussed about the basic principle. We have learned about that, and then we saw the different kinds of ultrasonic probes. And then in the last class, we saw this the different parts of the test equipment which is used for doing ultrasonic testing. Okay. So, we will continue on this and we will see the other aspects of this particular technique. So, in terms of the incident angle, we saw that there are two scenarios. When the incident angle is 0, then this goes vertically down like this, the ultrasonic waves goes into the sample in this fashion, and in some cases you need to send the waves at a particular angle like this. Okay, because there could be cases as I would have said before also, where the defects and flaws might lie at an angle, or the part itself is such that you need to send the waves at some angle. Okay. So, this is the scenario which is known as a normal probe, because the ultrasonic waves are going vertically down perpendicular, and this is an angle probe. Okay. Right. So, depending on what kind of part you have, and what kind of defect orientations you are expecting. So, based upon that you could either select a normal probe or an angle probe. Okay. So, when you send the waves at a small incident angle, so across an interface there is a possibility that if you are using longitudinal waves, there is a possibility that at the interface there will be some kind of mode conversion, and a part of the longitudinal waves will be converted into transverse wave, which are also known as shear waves. When the incident angle is more than 0. Okay. So, this is a scenario like this. If you have an incident angle, let us say alpha 1, okay, and let us say this encounters an interface between two medium. So, let us say this is medium 1, and it is going into another medium which is here. So, this is the interface. So, if you have an incident, a small incident angle at this interface, then there is a possibility that a part of this longitudinal wave that you have, okay, will be converted into shear wave. And across this interface, since now it is entering another medium, there will be a change in the path of this wave, okay, due to refraction effects. And let us say this is the velocity in medium 2 and phi L 1 is the velocity in medium 1. Okay. And as I said, a small part of this can also be converted into a shear wave or transverse wave. So, this is the transverse wave due to mode conversion. This is the longitudinal wave transmitted into the second medium, and this one is the transmitted transverse wave. Okay. So, when you are using an angle for doing the test, that means because of this mode conversion, two kinds of waves will enter the sample, longitudinal wave and shear wave. Both of these waves will enter the sample, and we have already seen that velocity of shear waves is lower than that of longitudinal waves. Okay. So, that means when these waves reflect back from an interface, which could be a discontinuity also, they will arrive at the probe at different time. Okay. So, that means the reflections from the same interface will arrive at different time, and you will see them on the screen on the display as the same signal appearing at different times, okay, because the velocity is different. Okay. So, this will confuse the examiner. Okay. So, this will create a confusion, and that is why it is always better to have only one kind of wave going into the sample and coming back to the probe. Okay. So, if you want to do that, when you have this kind of scenario, then you need to exclude one of these waves, and as we are going to see now, you have to exclude the longitudinal wave, and the reason for that we will see in a moment. So, in that case, when you do that, you have to send it at a particular angle which will ensure that only shear waves enter the sample and the longitudinal waves will be reflected back. They will not be transmitted to the sample. Okay. So, that will depend on the angle of incidence, and let us find out what that incidence angle is. Okay. So, let us say this is the incident longitudinal wave, and the velocity in medium 1 is V L 1, and then this is the transmitted wave, and this is the incident angle alpha 1. Okay. And as I said, a part of this will be converted into shear wave. So, this is the transmitted shear wave. Okay. So, if you want to exclude this transmitted longitudinal wave and only want to keep the shear, then you have to send it at a particular angle, and that angle can be found from Snell's law. Which says that the ratio of sine angles in these two medium, that is sin alpha 1 by sin alpha 2, will be equal to the ratio of the velocities in those two medium. So, this will equal to V L 1 and V L 2, wherein V L 1 is the velocity of the longitudinal waves in medium 1 and V L 2 is the velocity in medium 2. Okay. So, now if you keep increasing alpha 2 or if you keep changing alpha 1 such that alpha 2 increases, at some point alpha 2 will become 90 degree and be parallel to the interface. Okay. So, that particular angle where alpha 2 becomes 90 degree is known as the first critical angle. So, this corresponds to alpha 2 becoming 90 degree. Okay. So, this gives you the first critical angle as sin inverse the ratio of the velocities. Okay. Now, if your angle is little more than this, little more than the first critical angle, then this longitudinal beam will be reflected back into the first medium and it will not be transmitted. Okay. So, with respect to medium 1, then it will go through total internal reflection and nothing will be transmitted into the second medium. Okay. So, that means, if your angle is beyond first critical angle, then you can ensure that the longitudinal waves are not entering into the sample which is medium 2. Okay. But if you look at this, the shear waves, there also you could have an alpha 1 at which beta 2 will become 90 degree. Okay. So, the angle at which the beta 2 becomes 90 degree or the transmitted shear wave becomes parallel to the interface, that particular angle is known as second critical angle. Okay. So, this relationship between the incident angle alpha 1 and the transmitted shear wave angle beta 2 is given by again the velocity, the ratio of the velocities, that is V L 1, and this beta 2 corresponds to the shear wave in medium 2. So, that means, this is the velocity of shear waves in medium 2, which we will call as V S 2. Okay. So, the second critical angle, that is sin alpha second critical, corresponds to beta 2 becoming 90 degree. Okay. So, we have the second critical angle now. Which is sin inverse V L 1 by V S 2. Okay. So, if the incident angle is beyond second critical angle, then nothing will enter the medium 2, no ultrasonic wave will enter medium 2. So, that means, if you want to have only shear waves entering the sample, which is the medium 2, then the incident angle should be in between first critical and second critical angle. So, it should be greater than first critical and lower than second critical. So, it should be in between the first critical and the second critical angle, which will ensure that only shear waves enters the sample, and then you will do the inspection using shear waves, and the confusion that you had that the same signal coming back at different time, that can be avoided. Okay. So, in order to do that, you have to ensure that you have only shear waves entering the sample, and for that the incident angle has to be in between first critical and second critical angle. So, we will take an example and then see for a particular material what could be that angle. Let us say we have a steel sample, and we are using a probe which has this plexiglass face. Okay. So, the front face just in front of the active element, if you have seen the construction of ultrasonic waves, is some kind of fiberglass kind of thing is there, okay, just to protect it and also keep it inside that housing. So, many a times this face material which is in contact with the sample is made of plexiglass, and the sample is made of steel. Okay. So, that means our medium 1 in this case is the plexiglass, because the waves will first come out through this plexiglass phase, and then it will go to the sample. So, that is the medium 2, which is in this case steel. Okay. Now, if you look at the velocity of sound wave, the longitudinal waves in steel and in plexiglass, these are velocity in plexiglass is 2.67 kilometer per second. Velocity of the longitudinal waves in steel is around 6 or 5.95 kilometer per second, and the velocity of shear waves, that is Vs steel, that has to be lower than the longitudinal velocity. So, it is 3.2 kilometer per second. Okay. So, let us calculate the first critical angle and the second critical angle for a steel sample where the face of the probe is made of plexiglass. Okay. So, the first critical is sin inverse PL1 by PL2. So, that means this is VL1 is 2.67 because medium 1 is plexiglass, and VL2 is 5.95. Okay. So, this will give you an angle which is around 27.5 degrees, and the second critical is sin inverse VL1 by Vs2. So, that is sin inverse 2.67 by 3.2. So, this will give you an angle of around 56 degrees, 56.6 degree. Okay. So, that means, if you want to inspect this steel sample using an angle probe, so as I said, you need to ensure in that case that only shear waves are entering the sample to avoid that confusion. So, you need to ensure that incident angle is in between 27 and 56. So, an incident angle for this case for the steel sample, which is between these two. So, an incident angle like 40 to 45 degree will be good in this case. Okay. So, this will ensure that shear waves are only entering the sample and the whole sample will be inspected by these shear waves. Okay. So, this is how when you do the inspection by using angle probes, this is how you choose the angle depending on the velocity of sound waves into the material that the sample is made of. Okay. The next thing is how do you send these waves into the sample. So, when you do the testing, you take the probe. So, this is the transducer you have, this is the sample. Okay. So, you touch it on the sample surface and then you switch it on. So, the waves will be going into the sample, but at this interface, as you could realize, there is an air gap. Okay. And if this air gap exists, then there will be a decrease in the intensity of the waves, or there will be attenuation okay, into the air. So, you need to ensure if you want the entire energy of the sound waves going into the sample, and if you want to prevent this attenuation or decrease in the intensity, then you need to exclude this air gap before you could send the sound waves into the sample. Okay. So, in order to exclude this air gap, you need to apply something on this interface which will exclude the air. Okay. So, if you apply some kind of oil or grease or some gel in the form of a thin layer, okay, that will ensure that the air gap is excluded, and now this attenuation or the decrease in the intensity can be avoided. Okay. So, this particular thing which is applied to avoid the air gap is known technically as couplant. Okay. So, this couplant should satisfy certain requirements for it to be used effectively and for it to exclude the air gap. So, the couplant must be couplant must satisfy the following requirements. It should be as thin as possible, to avoid any alteration of direction of the beam. Okay, if it is a thick layer, then that itself would act as a different medium, okay, and due to the presence of a different medium, then as we have seen before, these sound waves will change their direction. Okay. So, in order to avoid that, you need to ensure that this is applied as a very thin layer, so that the direction of the beam does not change when it is passing through the couplant layer. Then it should wet both the probe surface as well as the sample surface. So, it should have good wetting or good spreading property. Then it should also be able to feel the small irregularities that you might have on the surface of the sample, so that it can provide a smooth surface for the probe to move on. So, this is another advantage you have when you apply this couplant. It will fill up all the irregularities on the surface, and it will provide a smooth surface for the probe to move. And it should not restrict the movement of the probe. So, it should allow free movement for the probe. And it must be easy to apply and easy to remove. And it must be harmless to the surface on which it is applied. Okay. So, these are the property requirement from a couplant for it to be used effectively. Okay. So, this is how when you do the test, you might have seen that some kind of oil or grease is applied on the surface, and then on that the probe transducer will be kept and moved over the surface. Okay. Right. So, this is all I will have for today. So, in the next class again we are going to see the other details of this process. So, for today I will stop here. Thank you for your attention.